My name is Andrew Haslett. I'm the chief engineer of the ETI. I'm a chemical engineer, not a mathematician, and therefore my answer to the question, which kind of mathematics are you an expert in, is neither. I guess at various times during my career, I've been very interested in applying mathematics to solve either technical problems and engineering problems, or more latterly actually business decision-making problems. And I've also had the corporate mathematicians working for me because people felt that I could connect them with the real world, because I saw their skills as being really quite important to create business value. When I was actually coming up with the equations and solving them myself as a junior engineer, I tended to be designing chemical plants, and therefore it was all about equations. I guess I first realised that I didn't understand, probably fair to say that my training in statistics was complete rubbish, because the UK education system doesn't seem to be very good at teaching people statistics, except for some kind of esoteric cookery with no logic to it. But later on I got a better input. I realised that uncertainty was important when I was trying to optimise the design of a big, expensive chemical plant to be built on Teesside, and I wanted to know how large to make some of the subunits in order to maximise the expected profitability of the plant over its life. And I discovered that we didn't really know with any great confidence what the future costs of our raw materials were likely to be, and if you examined the historic record of people making that prediction, they were useless at it. And if you looked at the market size and costs, price of the product, that was also badly predicted. And I got a lot of weather data, because atmospheric pressure and temperature were quite important for the physical performance of the plant, and I discovered just how difficult it is to represent weather data. So that was all quite a spur to thinking about uncertainty, and the fact that this very apparently deterministic process of optimising the design of the chemical plant is nothing like that at all. Okay, I have to press a button. Aha. Right. In my world, decision making is a social process. So you have a group of people who have some kind of decision to make, and you are there as some kind of assistant or expert or something, or facilitator, to bring together these techniques, mathematical techniques, whatever they might be, in order to help them make that decision. There is a natural cycle to this process, which if you're successful, they ask you back again and again, and you get more work out of them. So you engage with them to find out what is on their mind, what is the nature of the decision or issue they face. You start to help them crystallise that down as a group of people, at which point you often discover they don't agree what it is that the issue is and what it is they want to do about it, and that is part of facilitation. You then select whatever the methods are that you're going to use to explore, to optimise, to quantify, to characterise the issues. There is then often a huge amount of data gathering and opinion gathering. Notice that data has some objective reality, possibly, although you often find the opinion is that the data isn't very good, and that opinions can be really interesting because they're informed by something. You then apply the methods to the data, you perform the analysis, you then re-engage with the stakeholders to explain the analysis to them, at which point you discover that the discussion isn't necessarily about what is best for the group, for the business, but can also be about the extent to which the analysis confirms the beliefs or prejudices of the individuals, or the extent to which the consequences of the decision place liabilities or risk or accountability on the individuals. So that can be quite an interesting process in what is called socialising the decision or socialising the analysis. So that's how it works. And people often present these decisions as, let's make a decision, now let's defer the decision and gather more data. A famous business team failure in product development is to ask for more data in an uncertain environment in order to make a decision that in fact has no risk. Of course, everyone knows that in business you make a profit by taking risky decisions, and if you take decisions that have no risk, you're either fooling yourself that there is no risk, which is true, or you're failing to do your job as a business person. And if you see business as a series of private options, as I do, the context for decisions is always about the creation, exploration, exploitation of options, then, as people said to me when I talked to real option theory, as it was emergent, the decision to do nothing can often be the most valuable decision of all, but sometimes people formulate that as deferring a decision. It is a decision to do nothing. There has actually been quite a lot of research about decision making in a number of different fields. So there's research into the social dynamics of people making a decision. There's research into the nature of successful decisions, what they look like and what it is that determines the likelihood of the decision being successful, how have you judged success. And there's quite a bit of research into expert judgment and decisions formed by experts, which is quite scary. If any of you are interested in that, look at TNO Delph. So essentially you could summarize their findings. The more confident the expert is they're right, the more likely they are to be completely wrong. And I'd personally be most interested in the evaluation of individual decision making, because I think I'm an individual and I'm contributing to the decisions as an individual. And there are two pieces of work there. One, a very current piece of work looking at what are called super forecasters, people whose ability to forecast events or to make decisions, typically about investments, is factorially more higher than the mean performance, the herd performance. And also psychological research, or clinical psychological research, looking at people whose ability to make decisions have been damaged by some kind of organic malfunction or insult, an infection or a head trauma or something like that. It is entirely clear, if you look at all of that a good decision has two components or two processes which are very well represented in the human brain, because people, as somebody observed earlier, are actually quite good at making decisions, and the world is an uncertain place and people manage to navigate it somehow. And one element you might describe as the analytical element, and the other you might describe as the intuitive element. Sound a bit familiar? And again, if you go into that, the analytical element is about the ability to add things up, what we have had a lot of conversation about today. And the intuitive element is actually about making sure that you're answering the right question, the one which is pertinent, if you like, that you've selected the right methods on the right model. So crudely speaking, if you have a failure, if you have a bowl of fruit, it has 2 apples and 2 bananas in it. The failure of the analytical method is to come back with a judgment that there are 5 pieces of fruit because you can't quite get the number right. The failure of the intuitive element is to say that there are 4 pieces of fruit, when in fact the question was how many apples are there? And if you want to be a bit more subtle about that, the question is really how many of these pieces of fruit do I need to eat to meet my 5 a day requirement, and the answer is not 5. And you conclude immediately you've got the wrong data, because you don't know what the nutritional content of the apples and bananas is, or indeed what you mean by 5 a day, because 5 a day doesn't really mean anything, does it? So I have quite a bit of experience of working with people to make these kinds of decisions, and I would distinguish between experimental decisions, as we just had, the design of experiments, and design decisions. So when you're making a design decision, in a business you're often making design decisions. You're trying to do something which in its specifics has not been done before. You cannot go and do experiments on a system that doesn't exist. So you inevitably have some kind of conceptual and mathematical model of that system, and the question is how you decompose that into pieces and how you then reassemble the pieces into a system in order to make a decision about the characteristics of the system. And of course when you decompose it into pieces, you can often do experiments on some of the pieces. So I'm a chemical engineer, I'm designing a plant, it's a new plant, the design is different from plants that have been operated before, and as a research manager, which I have been, you then design laboratory experiments to test some of the components, and you use mathematical models to think about how they all work if you put them together. Right. So I am the chief engineer of the ETI. I turned up there 10 years ago at the beginning of its life as its strategy director. And if I had to simplify my job down, it would be to recommend to the board what projects we should do and what objectives or targets we should set for those projects. So we had a lot of money, as you'll see later, hundreds of millions of pounds in principle to spend over a 10-year period, and we were supposed to be doing that. This is a historical slide. This is what I found on arrival. Things have changed a bit since then. You'll notice the government departments are reorganised, and Eon ceased to be a member and then came apart. So this is on arrival what it looked like. And that's another thing, actually. As I once said to somebody, the problem with having business strategies and trying to do research and innovation to fit the business strategies is that the strategies change faster than you can get the research and innovation done. And at a certain point you decide to do the research and innovation that you should be doing, not the research and innovation you should be doing to deliver the strategy, because the research and innovation creates new strategic options. Back to options again. I don't think there's a great deal I want to say about that, other than that we were about developing and demonstrating technologies, by implication those material to the future of the UK. So I arrived and I thought, I'm the strategy doctor. I have to make recommendations to a group of people who are putting £5 million a year each, or £50 million a year up to, in terms of the government input, and they will have certain views, and this is going to be a bun fight. And I thought, well, it's always going to be a bun fight, but maybe if I can persuade them that we have some kind of analytical framework which creates some kind of objectivity and basis for discussing between them what the right answer is based on that process, then at least there will be less crumbs on the table and less blood on the carpet. And I was right. There was less blood on the carpet, crumbs on the table, but my God, it was still a bun fight. In order to do that, one of the core elements was an analytical simulation model of potential future UK energy systems. Technically it was a Monte Carlo simulation based on pretty much any parameter you wanted to be have a probability distribution, which created technology assets starting from the current technology asset stock and the current demand requirements and the current constraint requirements about carbon budgets, and then looked for optimal solutions under uncertainty into the future. And that informed our experiments, our projects, sorry, not experiments, and over time it became apparent that the projects that we were constructing had this framework. At least that's what we went back and told the board in order for them to see some kind of coherent structure to the projects. So we did tiny little projects that took up to 2 years and only a few £1 million. We did small projects of 5 to 15 £1 million that took a bit longer, and it turned out that they'd scaled the organisation wrong, that they found it really difficult to do those 20, 30 £1 million projects that took such a large proportion of the expected life of the organisation. It was quite difficult to manage making the decision and getting it done in time. As we started to do those projects, and we've done quite a lot of them, with number weighted towards the small knowledge building projects and cost weighted towards the large spending money projects, of course we're gathering a huge amount of data which we can now feed into an understanding of the subcomponents of our potential system, yes, but also we are advancing the capability, the body of knowledge, the commercial reality of some of those technologies. We are therefore interacting with the system in a way which means that we're not an observer. We are changing what is done, what the capability is, and what people's perceptions or beliefs are. At a certain point, somebody said, you know, this analysis was just something you had to do to perform your function, but actually the analysis has value in and of itself, because you can turn this upside down and say your function was to spend the money to move things forward, but actually it turns out your function is to spend the money in order to create the knowledge base, the momentum base, the capability base that informs what we want to spend our own money on. And at the time, our industrial and public sector members between them had an annual research budget of £6 billion. Obviously not all of it about climate change, but a non-trivial part of that £6 billion was spent on energy-related and climate change-related things, and they saw the traction of the analysis on that as being at least as valuable as spending the money. Of course, one of the benefits of spending the money was it created information which informed that. A very different decision-making process than they had originally expected. I could say a lot more about that, but I'm not going to. Okay, all of that sounds a bit conceptual. I could spend an hour telling you about different projects and how interesting they were and how difficult they were and what a bloody nightmare it is to get anything done when you're doing innovation with multi-party projects. I'm just going to show you this chart, which gives you some sense of the fact that we actually did things, achieved things, created things, got insight. And that's sort of interesting, and that is the chart that my CEO at the time produced for the board at the time, a year and a bit ago, to sort of project, at the end of this, this is what you got for your money, or will have got when we finished it. I'm going to come back to what I think, as it were, the analytical capability, what that was and how that worked next. But first, as they say, a commercial break from our sponsors. Unsurprisingly, McKinsey and people like McKinsey have studied business decision-making under uncertainty. And we've talked today about some quite narrow and specific business decision-making, like will my house be flooded? But this is really broad. What should I do with the assets of my company is the kind of question that if you're a senior partner of McKinsey, you pay your mind to because it's worth more money than worrying about whether an individual house is going to be flooded. Although, of course, there are a lot more houses, and it matters a great deal to people whether their house is going to be flooded, but CEOs tend to want to know what to do with the assets of their company. This is a very seminal paper by these people associated with McKinsey. I think Hugh Courtney was the McKinsey senior partner, about developing business strategy, which is, strategy is just where you place large chunks of capability or large strategic investments. It has a bit more context to it than that, but that is in the essence what you're deciding, given different kinds of uncertainty. Personally, I really like the original paper. Some of the expansions of it that they made later I don't actually agree with. Not that some of them I do. I think probably they were reacting to the fact that the kind of people that pay the money find uncertainty very uncomfortable because of the accountability aspects that you have if you're senior in a business and you make decisions. And therefore, to my mind, they made some of their examples a little more watered down or acceptable to people making decisions, a little more comfortable. So in the first level of uncertainty, you have a clear enough future. So you're planning the operation of a refinery that you've been running for years in a market where you've been buying the raw materials for years and you've been selling the products for years. And the question that your business planning function wants to know is, what can we expect from this refinery in terms of operations as a business unit? And you say, well, I've got a bloody good model, I've got lots of historical data. My problem is that I've got parameter uncertainty around the specific details of various things. And so what you do is you do a Monte Carlo simulation of this complex, well-established, well-defined model of your refinery, which gives you some sense of the range of profitability, and your accountant can do that for the whole company, and you hope that you know which things are correlated and which things are not correlated as between the different units of your business. And this is a fairly well-known piece of economic modelling, and you can therefore predict the cash flow and profitability of your company and how your treasury function should manage some of the hedging and issues around that. The second example I gave is your business is about to be subjected to a change in regulations. You know what the different regulatory models are that are currently going through the House of Representatives or Parliament or the European Union process or whatever it might be. There's a heated discussion about it. You're not quite sure when it's going to conclude. You're not quite sure exactly what model is going to be adopted, but you can see what the various potential models might be, what the nature of the political discourse around them is. You might choose to intervene in that process or just be a taker of the outcome of it. But you can now build a Markov chain model where you define a series of branching points in your business process, and you have these alternatives, and you can look at your strategic response to them, and you can start to model what the implications for your company might be, what kind of resources you might have to move around, what impact it would have on cash flow, and so on. So you now have a Monte Carlo Markov chain model. Excellent. And now we get up to a situation where it's a little less clear. And now we're into MySpace. So here I am trying to choose a set of technologies to invest in, which in some combination are likely to be material to a successful future UK energy system. And we are now moving from parameter and model uncertainty into what I would call ambiguity. So remember those two decision-making processes that you combine. One of them is the analytical, and you have uncertainty in the equations, the method for solving the equations, the parameters you put into the equations, and the other was whether you're solving the right problem. And I would define that as ambiguity rather than uncertainty. And you could argue that both of them are uncertainty in terms of the definitions that have been used this morning, or that only the model being uncertainty, the analytical uncertainty is uncertainty. I really don't care, because in making business decisions they're both important. Now you're moving into a range of higher ambiguity. And as somebody, in my observation, observing that there are exactly 4 pieces of fruit when the question is not actually how many pieces of fruit there are, isn't terribly helpful. So enormous investment in the detail of all of the elements, precision in solving them, and quantification of the residual uncertainty in them, is not very helpful if your problem is ambiguity. You don't know what problem you're trying to solve. In this Monte Carlo model called ESME, for modelling whole UK, well, actually energy system, but configured to model UK energy system futures, as a design exercise, as a prediction exercise. We did actually have a version that UCL put together for us, where it was a Bayesian network front end to it. By Bayesian network, I mean literally a belief network. So you could talk to different stakeholders and get their beliefs about the future of the world and what might happen given some of these political decision-making processes and consumer choices that have not yet been made. And you can show how different views or beliefs about the world can be connected together to create the parameter ranges and uncertainty ranges you put into your Monte Carlo model. It is a heroic piece of modelling because, of course, as well as having a large set of samples space defined by your particular set of technology parameters and your uncertainty parameters, you now have alternative scenarios of those, and you have to solve it many times in order to cover all of the future universities that you might believe in. It's quite a nice process because it has structure to it. I never used the tool, although the tool was developed and run to test it, I never actually used it to support any real decision. I probably would have done had I had a bit more time, because I think the way that people go about constructing scenarios has a very huge degree either of complete randomness or of heroic confirmation bias. They choose those things that suit the answer through the elements of the scenario. Whereas this is a process where it actually allows you to represent people's beliefs about the future in an objective way and then show how your different beliefs or views or statements lead to different conclusions and why that is. And then finally you get to true uncertainty. And the example that Courtney uses is before anyone put a mobile phone network into India, you were a global mobile phone company, and the question is, should we go into India and establish a mobile phone network, and if so, how? And he says, well, that is a true uncertainty. What are you, India is not the same as other countries, what are you basing your views about what that means on? All kinds of uncertainties, from can you rely on people to build and maintain the network, through to what will people buy and how will they use it when they bought it. In my world, everyone knows it's very hard to predict how consumers are going to react to a product of which they have no experience, and how people are going to behave in a world which has so many dimensions which are different that it's very hard to infer from their current behaviour how they're going to behave in the future. One of Courtney's very strong recommendations is you should not forget what you already know. So you should not start by assuming that because there is some uncertainty in the system, you should not think about those things which are perhaps uncertain. So one of the things I've chosen to do, we do a lot of consumer research, we try and give people simulated experiences of different kinds to find out how their understanding and engagement develops as they have different experiences. So that the fact that people eat and sleep and do other things, and they have done it for thousands of years, and to pretend that somehow that will be different is awful.
Excuse me.
Yes.
Your microphone's failed. I'm having trouble hearing you. Is someone that
Do apologise.
look into it?
Is that better?
Turn it on.
I think we have what's called a flat battery. I'll try and speak a bit louder, sorry. Yeah. Okay, so we have this high-level model of the whole system, which clearly does not have the granularity of representing every single person in the UK, or every house in the UK, or every conceivable variation of technology. It would just be too large. Is that better? Okay. And beneath that, we have more detailed models. So in one sense, as you run the more detailed model, it's a computer experiment in that element of the subsystem. And of course, as I said, beyond that, we actually go out and do physical work to develop and test and synthesized technologies. And there are a lot of those more detailed models. And one of the characteristics of the process that I believe in, that we followed, is to take a potential solution, a system that we believe in general terms might be a plausible future option for the UK energy system, that might satisfy the tests of being affordable, secure, sustainable, and to some extent the design of the system can predict equity, or at least the issues you need to manage to deliver social equity. And we go out and design it. So for example here we have the offshore CO2 transport and storage network for a world in which we have carbon capture and storage. We know how big the pipes are, the project phasing is in the numbers there, and there's some commentary in there about how you manage the irreducible risk and uncertainty of not knowing what the stores are going to do until you start developing them, and the fact you don't really know what they're going to do until you finish filling them. We don't just say, oh look, there's the answer. We go, okay, if we believe that is the answer, can we in some way objectify that? And what does that then tell us about how, if you wanted to deploy the answer, you would then need to deal with the further uncertainties, the further investment in understanding. And to some extent we've done that. We actually contributed to injecting brine into one of those attractive looking holes in the ground in order to find out what its injecting properties were. The top one is using what we know about current journey patterns to try and understand what that might mean for vehicle charging. And the right-hand one is I think the most complicated model we ever built, actually. Yes, it probably still is today the most complicated, which looks at splitting the UK into 150 something 50 by 50 kilometre squares and understanding the production, transport, processing and use of biomass within there, which was fascinating because it didn't behave at all in the way we expected from our high-level assumptions, and made us think again about the whole process of bioenergy production and use. Okay. Very few people actually go and probe in detail the space that the Monte Carlo process creates. They like some kind of very high-level view. In fact, they sometimes like a very high-level view which looks at the average of all of the outcomes, even when they are physically incompatible. So some of these systems are not compatible with each other. There is not a rational world where you have both hydrogen vehicles and electric vehicles coexisting in large numbers, because you have two networks and that's not economically effective. At some point you reach one of those branches where it goes one way or the other. And here we have plotted every single one of the 2000 scenarios set. So these are the designs that are cost optimum with a particular set of parameters from the individual probability distributions plotted in primary energy space. So primary energy space is the amount of solar radiation, the amount of nuclear fuel, the amount of oil, the amount of biomass, the primary energy that goes into the system. We had a long argument about what phase space to plot the outcomes in. And primary energy space is quite attractive because if you look with engineering judgment at the system, it's actually the primary energy use is moderately sensitive to the system design without being so sensitive that you're all over the place. And it has the wonderful characteristic that a terawatt hour of nuclear fuel is at some level comparable to a terawatt hour of solar voltaic electricity. Again, they're not exactly comparable. You don't end up with the problem of having a space whose dimensions are peculiar and you don't know how to compare them. They have a related metric. And what you can see is a result of an extraordinarily simple-minded cluster analysis in this space. So we're looking at spherical clusters with the frontier of what I would call an isopleth, a hypersphere, where the concentration at the face of the sphere is the same for different clusters. And we've rotated the hyperplane you're looking at. So there's about 15 to 20 dimensions in this hyperspace. So you're looking into about 10, 15 dimensions into the hyperspace. The hyperplane is the one that gives you the largest subtended area of the sample set. So this is the biggest dimension. The biggest dimensions are different. It's not any of the individual primary energy technologies. It's the hyperplane that cuts through them. And these are the clusters. So clusters centered on scenario 1189 is the biggest cluster. It has slightly over 35% of all of the scenarios within that cluster, within a reasonable, recognizable variant of 1189. And then we all go all the way down to cluster 10. And at cluster 10, we're still collecting 2%, so 40 other scenarios associated with the centroid. I think we got to nearly 80% of all of the scenarios in those top 10 clusters, and we played around with the concentration, with the cluster radius and so on for a long time, and judgment was used to determine that was the most effective way of representing the clusters. There's a balance between having everything in one cluster when they're recognisably quite different from each other, and having 2,000 clusters of one. That's sort of interesting. You can go and look at the centroids. One of the conclusions you come to is there is an incredibly high degree of uncertainty. Remember, we made certain assumptions as a precondition for running this. We only had variations of the probability distribution of the parameters as our uncertainty. There are other uncertainties for sure, in both ambiguity and uncertainty terms. A very high degree of uncertainty about what the right answer is. Or as Yogi Berra once said, forecasting is very difficult, particularly about the future. You look at that, and my conclusion is that you need a portfolio of options. You can't afford to invest equally in every possible idea or technology, and you can show that some of them are highly unlikely to be either material and or successful within the costs and time and risk you're willing to bear, but you simply cannot choose a set of things that you're going to make work. You have to have a set of things that you're going to try and make work, and as they are more or less successful, you have to refresh that set and gradually narrow down to the things that you're going to implement. So there's something there about the process by which you take your decisions forward. And the bottom here has plotted into that plane, or projected into that plane, I should say, the extent to which the individual technologies vary in their uptake in primary energy space. And again, you get some interesting information out of that. Who would have thought that nuclear wind and nuclear generation and offshore wind was so highly positively correlated in the economic outcome space? Right. We do something we call measuring the option value. So if you take a technology out, what is the difference in the mean or expected cost across all of those 2,000 outcomes of delivering a functioning energy system out to 2050? If you look at Lord Stern said that the cost of meeting the UK's climate change targets, the expected outcome was a 1% reduction in GDP in 2050, which isn't a lot. Actually, his range of expected outcomes was interesting, so it was from rather more than 1% reduction to positive, as in there are opportunities in climate change if your economy is aligned with them. We can't get it below 1%. If you assume real-world decision-making where people don't make optimum decisions, it's bound to be higher than 1%. I have to say the number's going up all the time because we're not making, so it's hard now to believe that it's going to be as low as 1 and a bit percent. You can then take individual technologies out and find out how much that adds to the expected cost. You can also get some sense of the cost distribution and how that might change, but then you need to run quite a lot of samples to do that. You only need to run 100 to get quite a robust estimate of the actual cost. If I was looking at a bit more subtlety, I'd want at least 1,000, probably 2,000, and I started off with the view it should be 5,000, which takes quite a long time to run. There are two biggies, two things which it's really quite hard to deliver a system that meets your requirements without. One is carbon capture and storage, and the other is a large increase in the production of UK bioenergy. You can produce systems that work without one or the other. You can even produce systems that work without both of them, but only by making some heroic assumptions about reductions in demand, principally effectively banning international air travel. And I know that there are people who believe that should be the right answer. I listened to one of them saying that we should plan to close Manchester Airport by 2027 a few weeks ago in a very large room in Manchester, and Andy Byrne went, yes, I understand. And I'm thinking, you don't agree, but you're a good politician. And then you can look at the other things, and you go, oh, I don't care about nuclear, it's quite small. And you say, yes, but if I crossed off all of the things I might do, even if individually they're quite small, I end up with a system where I haven't got enough options. So then there's a question about how you construct an efficient portfolio of options, and now you're back to stakeholders. You go to, and people say, I want to do certain things, I believe in certain things, and I don't want to do other things, even if you can persuade me that it might cost me money. I want to leave the European Union, for example. Or you can't persuade some people, there's always more than one view about any particular issue. So that then leads on to discussion, because of course things that people believe in and are willing to put time and energy in are more likely to be successful and reach an outcome, and that is part of the ambiguity. It's not an uncertainty, because it's very hard to understand how that process might work. Okay.
Questions?
Yeah, I'm involved a little bit in some of these large-scale infrastructure projects, particularly in district heating. And if there's one variable which troubles everybody, whether it's private or public sector, is demand.
Yes.
Major financial institutions simply won't invest unless they have a clear estimate of future demand. So I wondered how much demand is pulling your technology options into the future. If you get demand wrong, and there have been some spectacular cases of that seems to me a very big variable. I don't know if you agree with that.
I do agree with you. You're absolutely right. That is one of the central questions. Of course, we're not investing today in assets.
Right.
We're investing in developing the technologies, if you like, in coming up with better, cheaper district heating systems.
But for example, if people are too frightened to be near a driverless car, then demand will, like some of these social media things, they'll collapse overnight, and you'll lose your billions.
So I'm heroically agreeing with you on that, and we have spent quite a lot of money doing consumer research. So we have just finished a field trial where we've given 200 people for a few days each, perfectly ordinary Volkswagen Golf, petrol engine, a hybrid Volkswagen Golf that has a rechargeable battery and a petrol engine, and a pure battery electric Golf with no engine at all. They have driven them as part of their daily lives. We did quite a lot of calibration of their expectations and belief about these vehicles beforehand. When technically the term is called, they have a significant psychological distance because they have no experience of at least two of these Volkswagen Golfs. And then afterwards you remeasure their beliefs and expectations, their range of views by one of them actually. We've got 1.5 of the UK's top driver psychology research people involved. There are only 2 of them, so Gillian's part-time on the project and Stephen's full-time. We will draw some conclusions about that, about the likely trajectory of uptake of electric vehicles in the UK. And as far as we're aware, nobody's done that before. They've looked at people who are early adopters and their reaction, or people's thoughts about something you have no experience of. But unless you're giving people experience, we're also, as part of that, running a trial with 240 people where we're trying to find out what their reaction is to managing charging. Group of people not managing charging, they just do whatever they want. You have a group of people where they're told, this is the tariff structure. It's up to you, when you charge, but you will get more points if you charge here than here. Another group of people which is, if you allow us to charge your vehicle when we think it's the right time, and you tell us what you want to do with your vehicle, we will give you a reward, first of all, for allowing us to do it, and secondly, if we can show that against our model we would have made more or less money with the freedom you've given us, we'll give you a share of that saving. And again, nobody's really done that with mass market consumers. That won't tell us anything but very useful, but it will tell us what experiment we should do next time. Yes.
Right. So I look at your pictures and I see the huge amounts of money involved in making sort of right decisions or bad decisions. So I'm part of the Centre for Energy Systems Integration, which is an EPSRC funded project that fits somewhere in your picture. So I see up close a lot of the people are now uncertainty assessments and how kind of rough and ready and contradictory they are. So my fundamental question is that in order to do it better, then the problem always is that involves spending resource now. Yes. And resource now is actual money. Yeah, and they're very reluctant to spend actual money now to actually to reach a better decision. So whereas money in the future that we lose, it could be billions, but it's not like real money to them. So the reason that we can't make good decisions is that no one does the analysis of the value of better research in actually reaching better decisions. So do you have a view on that?
Yes, I completely agree with you. So, and this is related to the business changes its strategy faster than you can do the work to deliver it. So the classic real-world example is, given a free choice, people hugely underinvest in their pension and then are surprised that they haven't got enough money in retirement. Some people don't insure things even though they can't stand the loss. You're right, people's natural, many people, and it differs, that people are quite different actually in this view. There are other people who hoard money because they're terrified that they won't have enough money in retirement. There is a spread of psychological profiles, and I would say, and I have no evidence to support this, in general management are slightly more biased towards the short-term population average. So you're quite right, you take trivial sums of money, like a few £100 million, and you think that's a big sum of money, ask yourself how much a single nuclear power plant or a single offshore wind farm costs, how much money you're programmed to develop better batteries costs. Why on earth would you not create information to make better decisions about where to put your resources? And of course, when you do, I'm immensely privileged, and nobody else wanted the job. It was a wonderful job to have. Someone said, "Gosh, this is a great job. How do you get it?" I applied for it. There must have been lots of competition. No, nobody else wanted it. So you got the job immediately. No, the board spent forever trying to find somebody else. They couldn't cope with a single candidate situation. So they loved it when we did it, but they would never have paid for it as a conceptual argument. In fact, I remember my deputy said, "This is all nonsense. The value of the tools and the insight we're creating is far greater than any project you do." I said, "Yes, that's great, but don't tell anyone, because we'll have this huge argument which will stop us being allowed to do the analysis. Let's just get on with it since we have the freedom to do it." So you're quite right. It is a fundamental problem that people prefer to make things up as they go along and prepare.
Okay, thank you.